All right, everyone. I'm going to be talking about Lab 8 and specifically like reviewing the concepts in it. So, Lab 8 was about, uh, as it states here, the specific heat of solids, which is sort of a measure of just how much energy it takes to how much energy it takes to increase the temperature of the object, or decrease the temperature if you're taking energy out of it, right? But the first equation they tell you is Q equals C delta T, where like Q is some amount of energy, C is the heat capacity, not the specific heat. Keep that in mind. Delta T, and then and then delta T would just be the change in temperature. So like you may have also heard like Q equals MCAT, where like Q equals MC delta T, right? So if you see this equation, or if you've seen this equation before, this C is the specific heat, which is the heat capacity C divided by the mass of the object. Um, and so they define it for you down here. So this lab, we were specifically looking at the specific heat. We care more about the specific heat than the heat capacity in general because heat capacity depends on how much of the object you have. And so if we're really just trying to look at like, let's say gold, or I guess in this lab you used iron. So let's say if we're just looking at iron as a whole, like we want to know in general, any piece of iron, how much energy it'll take to increase or decrease the temperature. But if you have different amounts of iron, this like capital C will be different. And so if we're looking at like a general equation regarding any size of iron, we care more about the specific heat because it's an intensive quantity, while the capital C heat capacity is an extensive quantity. All right. And so the one of the other concepts used in the lab was something called latent heat, or the heat of transformation. And so this is like the heat or the amount of energy it takes for a phase change to happen. So in this lab, you were looking at liquid nitrogen evaporating. So the phase change was from liquid in the liquid nitrogen to gas or gaseous nitrogen, or N2. And so the energy is just equal to the mass that, like in this case, evaporated times whatever the latent heat was. And so you found later in the lab that the latent heat was around 200,000 joules per kilogram. All right. And so then one of the other equations you used was this Q equals Mn, this Q equals Ml, which like we know Q equals Ml from the last one. And then there's also the second part where this Ml is equal to Mc times the temperature of the room minus the temperature of the liquid nitrogen. And so what this is saying is, so you use this to calculate the latent heat of liquid nitrogen, because what you did was you measured how much liquid nitrogen boiled off, which was this Mn2, and then we told you M and C for the metal, or well, you calculated like you measured the M on the scale, and then we told you what C was for the metal, and then you used this to and then you had the room temperature and you subtracted the temperature of the liquid nitrogen. So what this is really saying is this MC is the heat capacity, right? So this is like how many joules of energy per temperature, or like per increase in Kelvin an object will be able to uh, take in. So like if your capital C is like 10 joules per Kelvin, this means that every time you increase the temperature of the object by 1 Kelvin, the energy that it absorbed goes up 10 joules. Or if you take away 1 Kelvin, then it goes up by, or it goes, then it loses 10 joules of energy, right? And so this T room minus Tn2 just says that we initially had a room temperature object, and then that object, the temperature went all the way down to Tn2, meaning that the change in temperature was T room minus Tn2. So that's why you were subtracting those. All right. And so this is like the same Q equals ML as before. And then the lab talks about the equipartition theorem, which just says that every atom in a solid will have a specific heat equal to Kb over 2, where Kb is the Boltzmann constant. You don't need to worry too much about it, but so it's equal to the Boltzmann constant. And then in a solid, the object can move in like the x, y, or z direction, but then it can also vibrate in these three directions. So that's 6 degrees of freedom. So 6 times Kb over 2 gives you a total specific heat of 3 Kb for each atom specifically. And this happens to be equal to 3 times R, which is about 25 joules. So theoretically, for like any solid, the specific heat should be 25 joules per mole Kelvin, or like specifically the molar specific heat, because the specific heat we've been talking about before is like joules per kilogram times Kelvin, or so joules per kilogram Kelvin. All right, so in the first part of the lab, you measured the latent heat of liquid nitrogen by seeing how much liquid nitrogen boiled off, and you ultimately ended up using this equation. And so here, like, this is the heat capacity of the material, C times M, and then this was the change in temperature. So I talked earlier about what that meant. And then we just divided by the change in mass of the liquid nitrogen. And that gives you the specific heat, which ends up being around 200,000 Kelvin. All right, and then the second part of the lab, we calculated the specific heat of iron and quartz. So earlier I said that we gave you C, and then you were calculating L using this equation. I misspoke. I meant like you had L from the last part of the lab, and so you used this L along with all these other things to calculate the C of the sample. And then Q2 asks, like, when will this equation not be valid? And there's like different ways you could answer it, I suppose. But like one example would be like if there is no phase change. So like here we're looking at a change in mass of liquid nitrogen, but if the liquid nitrogen doesn't change phase, then this wouldn't work. And then also like if like the temperature of the room is less than the liquid nitrogen, then you're actually going to be like absorbing liquid nitrogen from the air, which theoretically this equation could work, but you're also going to be absorbing other things like water vapor from the air and like other gases that have a higher freezing point than liquid nitrogen. So this equation wouldn't really work because we don't know how much of the weight increase in the styrofoam cup would come from the liquid nitrogen. So that's just two examples. I didn't answer question 1, but it was just about how closely the value compared. So theoretically, you should get 200,000, but if you don't, it's okay. Not every experiment is perfect, right? And then question 3 was like, how did the results obtained for the metal samples compare with 3R? So earlier, we saw that for any solid, molar CM, which is this, should be around 25 joules per mole Kelvin. Some of you found that it was close, some of you didn't. Again, not every experiment's perfect, but you will notice that there's going to be some variance due to just experimental error. And so question 4 was about how the specific heat of the rock sample compared with the metal. So you should find the specific heat of the rock sample is actually higher, which is fine, but the question is really like, why is that? So like quartz is like a more like mixed structure or like random structure, and so it's less conductive as well, and so because it's less conductive, it's going to have a higher specific heat, but that's not really like a good explanation. I think one of the interesting things about quartz versus iron is that so the iron is more dense, right? So iron is like significantly more dense than quartz, and it has a lower joules per kilogram specific heat. However, if you were to look at the like specific heat in regards to the volume, so like joules per like volume Kelvin, then you would actually find that iron has a higher specific heat in that case if you're looking at joules per like meters cubed times Kelvin. And that's because iron, although it has a lower joules per kilogram Kelvin, because it's so much more dense, it can store so much more mass in a smaller volume, that if you had like a 1 meter cube block of iron, which is huge obviously, and compare that to a 1 meter cube block of quartz, the iron would actually be able to absorb more energy, even though it has a lower specific heat in regards to mass. And then question 4 was how the specific heat of the rock sample compared with the... Oh, sorry, that's what I just answered, actually. So as I explained, like quartz has a higher specific heat, but iron, if you had the same volume of each, iron could actually store more energy, which I think is very interesting. And then the last question was about if you had like a composite material, like specifically you just had iron and rock mixed together, like what would the specific heat look like? Um, and so the answer to that is that it would be between the two, but where it lies between the two depends on how much of the iron and rock you have. So if it was like mostly iron and you put like a tiny bit of rock inside, then the specific heat would be essentially the specific heat of iron, and then vice versa. Like mostly rock, you would have the specific heat being very close to the specific heat of the rock. But in general, the equation for this is actually um, the sum over all I of MICI divided by the sum over all I of MI. So what we're doing here is we're saying that uh, we take the specific heat of like the ith atom in the uh, compound, and we multiply it times the mass of that atom, and that gives you like that gives you a heat capacity of the atom. But then we divide by the mass of that, and but then we divide by the total mass of all the atoms together. And so if you sum up all the heat capacities and you divide by the mass of, or you divide by the total mass of the compound, then you would get just the just the specific heat of the compound in total. And so that was really it for this lab. I think it was a fun lab, but just make sure you know uh, all the equations that you were using. Like, make sure you know this, and make sure you understand the concepts of heat capacity in general, like what it represents. Like heat capacity specifically is joules per Kelvin. So like how many joules something can absorb for every Kelvin increase, uh, or vice versa, or how many joules it gives away for every Kelvin decrease. And then make sure you understand specific heat, which is just dividing this by like the mass of your sample. So like divided by kilograms. All right. So just make sure you know those equations. Make sure you understand specific heat in general and like what latent heat is as well. And I'll see you at the LSA.